Hello! In this video, we are going to prove the following theorem. Suppose G is a group and A and B are elements of G such that AB is equal to BA. Then for all integers n, AB to the power of n is equal to A to the power of n times B to the power of n. Now let's remind ourselves how exponentiation works for elements in a group. Given any group element A to the power of 0 is the identity element of the group. A to the power of n plus 1 is equal to A to the power of n times A, for all integers n greater than or equal to 0. So this is essentially describing how we can take any group element and raise it to the power of a positive integer. So if we do A to the power of the positive integer n, then this should just be A multiplied by itself n times. So we know how to raise any group element to the power of a positive integer. So then how do we raise a group element to the power of a negative integer? Our definition is as follows. Given any negative integer n, A to the power of n is equal to the inverse of A to the power of negative n. And this definition makes sense because we know how to raise any element of a group to the power of a positive integer. So in particular, we know how to raise the inverse of A to the power of the positive integer negative n. So what's essentially going on here is it's telling us to multiply the inverse of A by itself negative n times. That's what we mean when we do A to the power of a negative integer n. And from this definition, we have shown that the inverse of A is equal to A to the power of negative 1, right? Which is the notation we're more familiar with for inverse of an element. So we can replace inverse of A with A to the power of negative 1 here. Now, another property of groups that we're going to be using in proving this theorem is the following. Given any group elements A and B, the inverse of AB is equal to the inverse of B times the inverse of A. Okay, so now let's get into proving this theorem. To start out the proof, let's say that the identity element of our group is E. Now the whole goal is to show that this equality is true for all integers. And we're first going to show that this equality is true for all integers greater than or equal to 0. And to show that, we're first going to prove the following claim. We're going to show for all integers n greater than or equal to 0, ab to the power of n is equal to b to the n times a. And we're going to show this by induction. So let's start with the base case. In the base case, we're trying to show that this is true in the case where n is equal to 0. So we want to show that ab to the power of 0 is equal to b to the power of 0 times a. So let's start out by writing the left-hand side. Now, we know that b to the power of 0 is equal to the identity element. And by definition of the identity element, a times the identity is equal to a, which is equal to the identity times a. And we know that b to the power of 0 is equal to the identity, so this is b to the power of 0 times a. So through this chain of equalities, we have shown that these two guys are equal. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0, and we assume that this equality is true for that arbitrary integer n greater than or equal to 0. And the whole goal of the induction step is to show that this equality is also true for n plus 1. So we want to show that ab to the power of n plus 1 is equal to b to the power of n plus 1 times a. So let's start out by writing the left-hand side. Now, by the recursive part of the definition, we know that b to the power of n plus 1 is equal to b to the power of n times b. But since we're working in a group, we know that the associative law holds, so we can move the parentheses around ab to the power of n. And then, by the induction hypothesis, we know that ab to the power of n is equal to b to the power of n times a. And then, applying associativity again, we can move the parentheses around ab. And then, we know that a and b commute. So we can replace AB with BA, and then applying associativity again, we can move the parentheses around b to the n times b, and then by the recursive part of the definition, we know that b to the n times b is equal to b to the n plus 1. So through this chain of equalities, we've established that these two guys are equal. And that was the whole goal of the induction step. So this completes the induction step. Because we've completed both the base case and the induction step, we've shown by induction we have that this equality holds for all integers n greater than or equal to 0. So now let's show that this equality is true for all integers greater than or equal to 0. And we're going to show that by induction as well. So let's start with the base case. In the base case, we're trying to show that this equality is true in the case where n is equal to 0. So really, we want to show that ab to the power of 0 is equal to a to the power of 0 times b to the power of 0. So let's start out by writing the left-hand side. Now we know by definition, ab to the power of 0 is the identity element. By definition of the identity element, we know that the identity is equal to the identity times the identity. And then from the definition of exponentiation, we know that the identity is a to the power of 0, the identity is b to the power of 0 as well. So this chain of equalities shows that these two guys are equal. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer, n greater than or equal to 0, and we assume that this equality is true for that arbitrary integer n greater than or equal to 0. And the whole goal of the induction step is to show that this equality is also true for n plus 1. So really, we want to show that ab to the power of n plus 1 is equal to a to the power of n plus 1 times b to the power of n plus 1. So let's start out by writing the left-hand side. Well then, by the recursive part of our definition, we know that ab to the power of n plus 1 is equal to ab to the power of n times ab. But by our induction hypothesis, we know that ab to the power of n is equal to a to the power of n times b to the power of n. So now, applying associativity, we're going to move these parentheses around b to the n times ab. And then we're going to apply associativity to move these parentheses around b to the n times a. Now, we have just proven for all integers n greater than or equal to 0, ab to the power of n is equal to b to the power of n times a. This statement works for every integer greater than or equal to 0. So in particular, it must work for the arbitrary integer n that we introduced here. So taking n to be n, we have that ab to the power of n is equal to b to the power of n times a. So we can replace b to the power of n times a with ab to the power of n. And now, by associativity, let's move these parentheses around b to the power of n times b. And then, by associativity again, let's move these parentheses around a to the power of n times a. So then, by the recursive part of our definition, we know that a to the power of n times a is equal to a to the power of n plus 1, b to the power of n times b is equal to b to the power of n plus 1. So, through this chain of equalities, we have established that these two guys are equal. So, this completes the induction step. Because we've completed both the base case and the induction step, this shows by induction, we've established that this equality holds for all integers greater than or equal to 0. So we have proven that this equality is true for all integers greater than or equal to 0. But now we want to prove that this equality is true for all integers less than 0. Now, to see how we can do that, the thing to observe here before we do that is that we could have performed these two induction arguments for any element of G, not just A and B, but if we replace A with the inverse of A, and we replace B with the inverse of B, we could repeat these same arguments for the inverse of A and the inverse of B. So we will end up proving for all integers n greater than or equal to 0, the inverse of A times the inverse of B raised to the power of n is equal to the inverse of a to the power of n times the inverse of b to the power of n. So now, let's prove that this equality is true for all integers n less than 0. To do that, let's give ourselves an arbitrary integer n less than 0. And to see that this equality is true, let's start out by writing the left-hand side. Now, since n is a negative integer, from our definition of negative integer exponents, ab to the power of n is the inverse of ab to the power of negative n. And since we know AB is equal to BA, we can replace AB with BA. And applying this result for groups, if we take capital A to be little b, and we take capital B to be little a, the inverse of BA is just A inverse times B inverse. So we get this. But now we're in a position to apply this statement, right? This statement works for every integer greater than or equal to 0. Now since n is a negative integer, that implies negative n is a positive integer. So if we substitute n with negative n, we have that the inverse of a times the inverse of b to the power of negative n is equal to the inverse of a to the power of negative n times the inverse of b to the power of negative n. So we get this. But then, again, according to the definition of negative integer exponents, a to the power of n is equal to the inverse of a to the power of negative n. B to the power of n is equal to the inverse of b to the power of negative n. So this is equal to a to the power of n. This is equal to b to the power of n. So we get a to the power of n times b to the power of n. So through this chain of equalities, we've established that these two guys are equal. And that proves for all integers n less than 0, ab to the power of n is equal to a to the power of n times b to the power of n. And with our two group elements a and b, we have proven for all integers n greater than or equal to 0, the equality holds. And for all integers n less than 0, the equality holds. So this equality must hold for all integers. And so this completes the proof. And so yeah, that's pretty much it for this video.